Welcome to CSAI Think Tinker Learn. This is part of my System Design Essential series. The goal here is to give you a solid mental model of a system design topic. We are breaking down the time series engine today. This is a concept first introduction to help you build your system design foundation quickly. If you want to see a deep dive on the trade offs or a specific case study, or if you want to talk about any of the topic that we discussed in this video or in some other video, do leave your message in the comments and we'll pick it up. Okay. And if you want a detail, if you are a person who want to go through the text in much more detail, please look out for the description. I have a link there for my website. These are the GitHub pages, so you can visit them for a much more deep dive article on these topics, and there are other system design related topics. Okay, let's move on to why a billion points a day breaks traditional databases. Next, go. Okay, to build a time series engine, you have to master the structural vocabulary. A metric has three parts. First, the timestamp, the physical anchor of the data. Second, fields. These are the unindexed raw values like temperature that change constantly. Third, we have tags, index metadata like host or region used in where clauses. But beware of the high cardinality trap. If you make a unique value like a user ID a tag, it blows up the inverted index and crashes your performance. It has over 100,000 unique values. Make it a field instead. Why do B trees melt? It comes down to random writes. A well-tuned SQL database like a PostgreSQL hits a wall at around 100,000 writes per second because of write amplification. The cost of constantly rebalancing deep index nodes. Modern time series databases cheat physics by using the sequential write. By appending to the end of a log and avoiding rebalancing penalties, they can sustain 1 to 2 million writes per second on similar hardware. The engine behind this speed is the log structured merge tree or LSM. The core insight is elegant. Don't organize data as you write it. Write fast, organize later. Step 1. Buffer everything in RAM in a mem table. This is unbelievably fast. Step 2. Once full, flush the data sequentially to disk as an immutable sorted string table. Step 3. Use a background process to compact and merge these files, cleaning up the mess while the front end keeps racing. We achieve 40:1 compression ratio by exploiting the natural structure of time. For timestamp, we use delta of delta, storing only the tiny offset between the regular intervals rather than full 64-bit Unix timestamps. For values, we use Gorilla compression. Since consecutive floats share most of their bits, an XOR operation reveals only the delta, allowing us to discard the rest. Data that doesn't change shouldn't cost you storage. Partitioning in a TSDB is about dividing the timeline. A single logical table scaling billions of rows for yesterday's data will always time out. The solution is time-based sharding. We physically isolate data into time-windowed vaults or chunks. This creates perfect write locality. All current lights land in the newest vault with zero contention against historical reads. Plus, TTL is trivial. To delete old data, you just drop the entire file. Never use row by row delete commands in a TSDB. Finding needles in billion point hated stacks requires two specialized tools. The Bloom filter is our probabilistic bouncer. It can instantly confirm if a series is not in the SS table, preventing 90% of useless disk reads. The inverted index then maps your metadata tags to specific series keys. Remember, the fastest disk I/O is the one you don't have to make. Never scan what you can possibly skip. Storing a year of 1 second granularity data is an architectural failure. It's too expensive and slow. We use an aging pipeline with continuous aggregates. Raw 1 second data is pertained for 7 days. Meanwhile, background processes create 1 minute rollups for 30-day retention and 1 hour rollups for indefinite storage. Your dashboard queries should always hit these pre-computed rollups, never the raw data tables. At scale, the architecture must be distributed. We use Kafka as a buffer to handle back pressure from millions of agents. The critical design choice here is the sharding key. It must be a combination of time and the series key. This ensures all data for a specific metric in a given time window lives on the same physical node. Our CAP theorem stance here is strictly AP, availability and partition tolerance. It is better to temporarily lose a few data points than to let your entire monitoring system go dark. To wrap up, keep this TSDB diagnostic matrix handy. If your writes are slow, check your LSM tree compaction. If your compression is poor, your data might be too erratic for Gorilla XOR. If your queries are slow, you might be spending too many historical shards or hitting the high cardinality trap in your inverted index. Now, for the community, what is the highest ingestion rate you have ever had to manage, and did you stick with the general purpose DB or move to a specialized time series database? Let us know in the comment. If this episode helped you, please like, share, and subscribe to the CSAI Think Tinker Learn. See you in the next one.